Okay, so on the way in today, you should have picked up this one that talks about more on horizontal asymptotes. Okay, I want you to read about, it says read about the properties of rational functions on page 364. I'd prefer right now you read about this. I've tried to make it even more clear right here for you. So if you'll read through the front of this page and ignoring the problems I've given you to try, okay, and the back of this page, that'll help guide you a bit today. Okay, so go ahead and read that right now. All right, so let's go through this page, read about it here, and then we'll be able to answer these questions. Horizontal asymptote tells approximately where the graph will go when x is really big or really small. Now, we're talking about a different asymptote than yesterday. Yesterday, we were dealing with vertical asymptotes, which we'll still deal with today. But your horizontal, remember, is moving left to right. Okay, it's crossing the y-axis. Or you could have a slant asymptote. Okay, so we're not dealing with the discontinuity when we're talking about this of your denominator. Okay, everyone with me on that? All right, so your horizontal asymptote tells you approximately where the graph will go when x is really big or really small. It is possible that your graph will sometimes cross over it. Okay, so it's a little different than x, where your graph will never hit the x asymptote. Your y asymptote, your graph could actually hit it and could cross over it a bit. Okay, when you're trying to figure out your horizontal asymptote, the first thing you should do is compare the degree of your leading exponents in the numerator and the denominator. That's huge. So as you're looking at this and you're going, here's my rational function. It looks like a mess. What you should look at is your leading exponent here is a 1. Okay? The coefficient is 1. Down on the bottom, it's 2. Your coefficient is 1. Okay? So when you're comparing your leading or your degree of your exponents there, and you say, well, look, it's bigger on the top or smaller on the top than it is on the bottom, okay, or the degree is larger in the bottom, okay, then that's going to make this fraction really small. So I don't expect you to just take that away and go, yeah, I get it. Well, think about values for x for a minute. Let's say we make x a really big or really small number. So like a really big number, maybe like 1 million. A really small number for x, maybe like negative 1 million. Is everyone with me? So what we want to know is, as we graph these things, and we're trying to figure out where our graph is approaching as x gets really, really big. So in other words, as we keep going this way on the x-axis, we're wanting to know, hey, what number is this, what value of y is this approaching as this graph keeps getting bigger and bigger? And same thing on this side. You know, if we're over here and we're going, okay, as my graph gets smaller and smaller, which value of y is it approaching? So if I'm going this way on the x-axis, I'm going big negatives. That's what we're trying to figure out, is what value of y we're approaching when x is really big or really small. Okay, so if I pick values here, so let's just say for a minute I have my x squared plus 3 over my x squared minus 9. Okay, sorry, that's not an x squared, that's x to the first. Okay, and I have y equals here, and I'm trying to figure out exactly what my y asymptote is. Okay, so I'm going to put in some big values to figure it out. So, you know, if I'm looking at my graph here, I have no idea what this graph looks like, but if this was the graph, I would say, okay, well, let's say go out to like 1 million. Why? Because that's huge, man. That's a big number. If I plug in 1 million for x, what does y give me? What do I get for y? So as I do that, if I have 1 million, like you have $1 million, okay? You have 1 million. You've substituted that in for x. Well, 1 million plus 3, does that change our number much, that extra 3? Not really. I mean, it's 1 million. Like you have $1 million, your buddy asks to borrow 3, you're like, dude, yeah, here's some chump change, man. Here you go. We're good. All right. Okay? Not me. I'm frugal. I'd be like, dude, you better pay me back. Come on. Hook me up. Sheesh. All right. No, it's 1 million. Okay? So the 3 is kind of trivial right now when we're dealing with that big of a number. And in fact, on the bottom, when we look at it, that's 1 million squared, which is really big, right? That's 1 with, rather than 6 zeros, you now have 12 zeros. Which is, holy shnikes, that's million, that's billion, that's trillion. That's 1 trillion. A million. You got a trillion. Our national debt, by the way, up around the teens, trillion, 16 trillion. Okay, just so you know, 16 million. Anyway, we don't need to go there. However, that's really big. Okay, so does the 9? I mean, I'll be like, okay, here's $9. All right, whatever. So really, the extra piece we're adding on to the end, that's chump change compared to what you have here. You have a million divided by a trillion. Is this fraction 1 million divided by 1 trillion? Holy cow. Could have picked a smaller number. All right, is that really big or really small? Small. Yeah, that's like way small, right? Yeah. I mean, look, we cancel some zeros. Well, I've canceled the wrong zeros there. I don't even know where to go with that. There we go. There. Okay, I have 1 over 1 million. 1 millionth. That's how small it is. That's like way small. What does that tell me? It tells me that my number that I'm approaching is what? Very small, or it's really, really close to what number? 0. Okay, so if you look at this, and what we want to do is start generalizing this. And we could do this for all of these here. But, I mean, here you have a million over a trillion. Okay, well, that's really small. That means we're approaching 0. My y asymptote right here is y equals 0. Here, I have a million over a trillion again, right? From this piece, I get how much? About. Well, it's 1 millionth, which is really close to what? 0. So essentially, you're getting 0 contribution from there. But then you have to add the 2 on. So really, my y asymptote is 2. Okay. Here you have, once again, 1 million over 1 trillion. The fraction part gives me a really small number, close to 0. And then what am I doing to that? Subtracting 3. So my asymptote's at y equals -3. That is how you figure out your y asymptote. Okay? Now that's just the very basics of it. So just right here, questions on just this part. Yeah?
So when we're finding the y asymptote, like for example, like another problem?
No, just, is it going to have a...
Plug in that?
You can. Let's remember, we compared the degree of the leading. If your degree is larger in the denominator, that's what we're dealing with right now. So everyone tell your neighbor what you're comparing right here, because that's key. Yeah, I mean, it only works for part of it. You got to compare your degree. If your degree is larger in the denominator, this is the pattern. Okay? Did that answer your question?
No, is it just like coincidence that it's the same as your outside term, like the +2 and the -3?
No coincidence. Yeah. You guys, it'll always... So if your degree is larger in the denominator than the numerator, your asymptote's always going to be your k value. Always. No coincidence there. So here we just had +0 out here. It's your asymptote. Because you're not getting any contribution from the fraction. Okay, or a very minor one. Okay? Everyone rate themselves 1 to 5 right there. Okay, so you got to look at 2 different contributions, the fractional contribution and the constant contribution. You have a fraction plus a constant. A fraction plus a constant. What are you getting from the fraction and what are you getting from the constant? Here I got nothing from the fraction, or really a trivial amount, a 0, and there's no constant, so it's 0. Here I got nothing from the fraction, right? It's essentially 0. But I got 2 from the constant, so it's 2. Here I got nothing from the fraction, and I got -3 from the constant, so it's -3. Yeah?
Well, is there an instance when you do get something from a fraction?
Dude, I'm glad you asked. We're going to move on. Yeah. Okay. All right, well, let's go on. Next piece. If your degree is the same, so you got a little star up here. That was if your degree is larger in the denominator. Well, if the degree is the same, so now you have this over this. Notice the powers are the same. This over this over this, that over that. Okay, the powers are the same. So when I'm looking at that, if I look at letter A, and I kind of go through the same process, and I now have 2 times x squared, and let's say x again is 1,000,000, and we square it, that is 2 times 1 trillion. I really don't like writing all these zeros, but I think it really helps. So I have 2 times a trillion minus 1. Who cares, right? Maybe we take whatever. Okay, we don't care. And it's 1 when you have 2 trillion sitting there. Sheesh. You know? And then, so we just ignore the 1 because it's trivial. And then here on the bottom we have 1,000,000 squared or 1 trillion. I don't know if that's enough zeros. Let's see. 3. That's not enough. How many more do I need there? 3 more. Thank you. All right. So 1 trillion, and then if I have a trillion and I subtract 2 times 1,000,000, how much is that? 2 million. But you have a trillion, right? I mean, that's a million. Like, so does 2 million matter? No, I mean, it's 2 million. And who cares? Just, I mean, whatever, you know? So, hey, we're just going, you have a trillion, okay? You just, like, give it away. You're like, dude, take some of my million. I don't care, okay? So I have 2 trillion divided by 1 trillion. What amount am I getting from this fraction? Yeah, you're really getting 2 over 1. And the way we get that, well, this is 1 times a trillion. This is 2 times a trillion. This is 1x squared. This is 2x squared. The contribution you get from your fraction here is 2. You compare your coefficients, they're the same, so you just divide the leading you compare your powers, they're the same, so you divide the leading coefficients. That's the piece you get there. So like if we do the same thing on this one, up here you get a 1 trillion, we ignore the 1, we're going to ignore all this other stuff. Powers are the same. You have 1 trillion and 3 trillion, which gives you 1 over 3 or 1/3. Here, y equals 2. Here, y equals 1/3. Tell your neighbor what y equals here. Y equals 4/3. And right here, you get 5 over 1. So you get 5 from that, but then you get plus 3. So y equals 8. How many got it? What are you comparing every time? First thing you need to compare so you know what you're doing, where you're at. Yeah, the exponents first and then the leading coefficients, right? Because that's key, because the next piece says if the degree in your numerator is bigger than the denominator. So you have 3 situations. You have the degree is larger in the denominator, you have the degrees are the same, and then you have the degree is larger in the numerator. Those are your 3 situations. Okay? If that happens, you have an oblique or slant asymptote. That means it's not going horizontally like these lines. It's going this way or that way. You have a slant asymptote. And how do you find that? Well, you look at it and you go, oh, power. Man, I've got 1 trillion divided by 1 million. Well, a trillion divided by a million is a million. Well, dude, that's not going to help us right here. We need to know where my asymptote is here. Okay? We're getting a huge number right here, and it keeps getting infinitely bigger. Right? I mean, if we keep changing x, our asymptote never stops getting bigger on there. It keeps growing. So what we do is, if the degree is bigger here, we do polynomial long division. our friend polynomial long division, where we say the bottom number, x minus 2, goes into x squared plus 3x plus 2, and we do the math. Now, the math's already done for you on here, right? Okay? All right, so we do this, and we get through all this, and we end up with x plus 5 and a remainder of 12. Now, remember when we did this earlier in the year, I said, hey, we're not going to call it R12. We're going to say plus 12 over what? X minus 2 over this thing right here. We make that our denominator. Well, now that you've started dealing with these, this piece right here is that front part. This is the back part. What's my h value? Well, h is 2. What's k? X plus 5. My asymptote is y equals x plus 5. What does that mean? It means you graph that linear equation. And that becomes your asymptote. So you go, well, my y-intercept, y equals mx plus b. Remember the back in the fun times of math where you're like, all right, man, 1, 2, 3, 4, 5. You plot it, you rise 1, you run 1. You're like, oh, these were so tough, dude. I remember doing these back in 7th grade, and I hated it. And that is your slant asymptote. That is the line your graph is approaching. Okay? How many are with me still? 3 different situations. Any questions? We're going to see some of those today. So in general, summarization on the back here. This is all online, or it should be if I can get it to work today. Okay? Set the denominator equal to 0 and solve to find, okay, that tells you your vertical asymptotes. Everything else is the domain, which means everything else is your x values. Anytime there are 2 vertical asymptotes, then there will be 3 pieces to your graph, which you'll see today. To find your horizontal asymptotes, so this is vertical up here, your x equals. This is horizontal here, your y equals. Oh, thank you. So vertical up here, x equals. Horizontal here, y equals. To find your horizontal asymptotes, compare the degrees of the numerator and denominator. If the degrees are the same, your asymptote's at the numerator's leading coefficient divided by the denominator's leading coefficient. Plus, you could add out in the side there, you could put plus any constant. So, like, the only thing you have to worry about is any constant that might be out here. Okay? If the denominator's degree is greater by any margin, okay, it doesn't matter what margin. So if it's x to the 7th power on the bottom and x to the 1st on the top, doesn't matter. As long as the denominator's degree is larger, then your horizontal asymptote is at y equals 0 plus any constant. If the numerator's degree is greater by by a margin of 1, then you have an oblique slant asymptote. If it's more than that, then we have other things we deal with, but you won't get to that this year. Okay? Which you have to use polynomial long division on. Okay. So we just got way more difficult very fast today. Like yesterday, you were like, dude, this is like the easiest thing ever. Chapter 8, those other guys don't know what they're talking about. Okay? This is like much more complex. Much more abstract. All right, tell your neighbor what you learned from this page. Okay, time's up. Any questions at all? I think it'll get easier as we start applying it. Okay? Matt, are you okay? Yeah. All right. All right, so here we go. Let's take a look at this. Read about the property. Okay, we've kind of done that. What's the greatest number of horizontal asymptotes we can have then? The most horizontal asymptotes. Greatest number is 1. Okay? We can't ever have more than one horizontal asymptote. Now we can see more than one vertical, but you can't have more than one horizontal. And the reason why is because, remember, when we're figuring out the horizontal asymptote, you're actually you're trying to find out what y does as you approach large values of x's. Okay? So you can only approach large values of x and small values of x in one way. You can't do it multiple ways. And remember, with vertical asymptotes, you can make the denominator equal 0 multiple times if you have multiple pieces on the bottom. So if we have like 1 over x minus 2 and x plus 3, or excuse me, let's use x minus 3 there. Okay? That's a bad looking 3. There we go. Okay? That means I have a vertical at x equaling 2, x equaling 3. We've done that. Okay? But there's no possible way to get a y-asymptote appearing more than once, because you can only approach really large and really small numbers once for y. Yeah.
Maybe this should wait till we graph them, but like, would you write in both of those x asymptotes?
You would, yeah, and we'll see that today. By the way, what would your y-asymptote be here? Tell your neighbor.
0.
Okay, time's up. What contribution are you getting from the fraction? Is the power greater on top or bottom? Bottom. So what's my y-asymptote?
0.
It's 0. You're getting nothing you're getting 1 over a trillion, which is really close to 0. So y equals 0. Okay, that being said, let's graph some of these. All right, you picked up a piece of graph paper on the way, and you're going to use that for today's assignment, and we're going to graph these on here. Okay, so this is what I'm going through, and now I'm not going to spend the whole time just graphing on this page, I don't think. Here, I think I'm going to use the same grid you're using because I like your tables better on there. So, some of these label vertical asymptote on your tables, and you can just cross that out if you don't, because sometimes there's going to be multiple vertical asymptotes, so really just cross that out. I just didn't have ones that didn't have it on there. Okay? So, first thing that we need to do, okay, and I'll start filling out maybe some tables. Well, you guys have that. I'll do it on here. Okay? First thing we need to do, we need to ask ourselves, what is our x equals asymptote and what is our y equals? And then you start seeing this thing called a hole. We're going to talk about that here in a minute as well. So have your note page ready to take notes on it. Okay? So go ahead and copy down your problem. You should always write next to your graphs, x equals, your asymptotes, x equals, y equals, and you may want to add that thing where it says a hole, because you're going to have holes in your graph today. They're going to appear, or disappear, I guess. Depends how you look at it. Then again, if it disappears, you can't look at it. So that's kind of weird. All right. Tell your neighbor what your x asymptote is and your y asymptote. Okay, here we go. Let's start with the easy one. What's the y asymptote? 0, right? Power's greater on the bottom, and it's 0. Now, how many got 0 for the y asymptote? Escalante. Power's greater on the bottom. Okay. Anyone get the vertical asymptotes? Hannah?
Oh, we were thinking that would be plus minus 2.
Plus minus 2. Anyone else thinking that? Oh, let's factor this, right? X plus 2. X minus 2. Now, some of you may have just set it equal to 0. Anyone just set it equal to 0 and solve? Now, here's the problem with that. We miss our holes then. Because remember when we were doing the factoring earlier on, I said, look, you're going to get this equation, and you're going to factor, and then what can I do with this fraction? Here's a hint. I can simplify. What can I cancel out of top and bottom? X minus 2. Now, when I cancel that out, I am removing that from the equation. A hole is called a removable discontinuity. Yeah, we call it a hole. It's a removable discontinuity. The only reason I use that term is because you'll see it in a book, but you also see that you remove something here. Which 0 did I remove? I removed 2. So my hole's at x equals 2. That's what I removed. Okay, sorry, this is really hard to read, so let me write it down here. Removable discontinuity. Yeah. Also known as a hole. That's what I will call it most of the time. Okay? What is remaining? X equals negative 2. Yeah, this piece. That 0 is remaining. That is my x asymptote. Now we think you got it? Now here's the cool part. This thing that looked like an expression on steroids a second ago, they're bad for you. Okay? But that thing that looked like an expression on steroids, we just reduced. We reduced it to 1 over x plus 2. Which is nice because when you're plugging in values for x, you get a choice. You can plug them into this one, or since this is equivalent, you can plug them into this one. Now, personally, I'm plugging into this one. Okay? Now, I'm just going to pick values for x and solve for y. That's the easiest route, I think, to go. That seems to be what the general consensus is. And since I only have one vertical asymptote, I'm going to put that right in the middle. Okay? I'm going to put my negative 2 here for x. Why? Because that's my vertical asymptote. And I know that's going to give me what for y? Undefined. Okay? And then I'm going to pick some values on either side. So here I'm going to go ahead and say, what do we want to use? Doesn't matter. Use whatever you want. Negative 1? That would be on this side. Okay, negative 1. What do we get? Negative 1 plus 2 is? 1 divided by 1 is 1. All right. Give me another value to use. I'm going to use 0. What's 0 give me? It's just easy, right? Because that disappears. Just 1/2. I like 0. It's my hero. Okay. How about if I put negative 3 in? 1 over negative 1, which gives me negative 1. What if I put 4 in? Negative 4. Negative 1/2. Okay? Now you only have to have 5 points. Okay, unless we have more branches. I've given you places where you can do 10 and negative 10. If you put 10 in, you get 1/12. Okay? If you put negative 10 in, you get negative 1/8. No, 5 points are fine with me. Okay, as long as you only have one vertical asymptote. If you have more than one vertical asymptote, you need 3 points in between each asymptote. Okay? All right, so here we go. We're going to graph it. We have a hole at negative 2, or 2. We're going to ignore that. We're going to go to x equals negative 2. We put our asymptote. Yeah, man. Okay, and then we're going to go to y equals 0 and put our asymptote. Graph our points. Negative 4, negative 1/2. Boom. Boom. You can even say boom. Negative 3, negative 1. Boom. Negative 1, 1. Boom. And 0, 1/2. Boom. And now, it really is tough to see there. Like, you're like, oh, what? My graph's just this? What? My graph's just this? That's why plotting, like, sometimes doing those 10s and negative 10s help out, because we know negative 10 is at negative 1/8, which shows that, hey, yep, you're approaching that line, which we know we should be. So once you have those points, you need to bend it off and have it approach those asymptotes. So don't just stop there and go, oh, I'm done. You got to keep approaching the asymptote. By the way, anytime you have a 1 on top, this number right here, you're always going to be over 1 up 1. You should be from your the center of where your asymptotes cross. You're going to start seeing that. As this top number changes, this point moves away. As it gets bigger, it moves away, or gets further from 0. If it gets closer to 0, it moves in. Okay? Starts fluctuating. Okay, now, I messed up because I put circles there, and I didn't want to put circles. I should not have done that on here because we have a hole. We have a hole where at? At 2. And the way we do that is we draw a hole at x equals 2 on our graph. So not actually on the 2, but where our line crosses x equals 2. You should have a hole. And you guys are using pencils. Just erase that part of the graph and put a circle there. That's your hole. Okay, these were the points we plotted. The open circle is the hole. That's how we show it. Questions? How do you think you got it? Easy McCheesy? All right. You guys don't seem too impressed. I'm pretty impressed. Let's go on to number 12. Number 12. Give it a go. Okay, everyone take a look back at your last graph. What's your question?
Why is there a hole at 2?
Because that was our removable discontinuity. That's what we canceled out.
Oh,
Okay? So that gave us the hole at 2. Any other questions? All right. Give it a go. The next one. Okay, hey, let's talk about this real quick. You guys, so first thing, let's do the y asymptote because that's the easy one. Okay? First power on top. What's the power on bottom? If you were to multiply this out and get rid of the parentheses, what would it be? Second. So the power is greater on the bottom than the top. What's that mean in terms of this contribution? It's at 0. Okay, this would be like 1 million or negative a million over a trillion. Okay, so we get 0. Really close to 0. How many got the y part correct? Okay, now when we're looking at this part, the y equals negative x over x times x minus 1. In this piece, we're saying, okay, I've got this part right here that tells me x equals 1. Okay, that would make that 0. That would be a discontinuity. And then I've got this piece that if I'm multiplying by, so if this equaled 0, x would be 0. So those are my two discontinuities. Can I remove either of them? In other words, can I cancel anything?
Yeah.
Yeah, this is like having negative 1 times x on the top. So the x's can cancel. So I have a hole at 0 at this one, the one I canceled. I have an asymptote at x equals 1. Okay, so I end up with a reduced fraction of negative 1 over x minus 1. That's the equation that I am going to plug my values into because it's easier than this equation. Okay, so I'm going to put my asymptote right here in the middle. Okay, this is undefined. Any questions up to there? How many made it pretty much that far? Or close to it? You got hung up a little. Any questions? Okay, so we put our asymptote at 1. Okay, and I'm going to let you guys finish the graph from there on that one. Okay? Just plugging in values for x, solving for y. So pick a couple on this side, maybe like 2 and 3. A couple on this side, maybe like 0 and negative 1. If you want to try 10 and negative 10, so you make sure that they're going off in the correct direction, it's a good idea. All right. We're going to pause there. I want you to go on to number 13. So that one becomes part of your homework tonight. 13, check it out. That means you need to stop with 12 because 13 becomes a little different. Okay? Go ahead and tell your neighbor what your y asymptote is. Volunteer, what's the y asymptote?
0.
Yes. 0, good. So we have x to the first on top, and if it makes you feel better, to rewrite that, you could say y equals negative x plus 5 if you want to rearrange that over x squared minus 1. And so now you look at it, you're like, well, power is greater on the bottom, so y is 0. Okay? X asymptotes. Can this factor? Yes. What's it become? X plus 1, x minus 1. Okay? So I now have y equals negative x plus 5 all over x plus 1, x minus 1. Can I cancel anything? Nope. That means I have an asymptote at x equals at negative 1 and positive 1. X equals 1 and x equals negative 1.
You say x equals plus minus 1.
Or you could say x equals plus minus 1. Those are your asymptotes. So no hole in this one. Notice I have tons of lines on my grid, and that's because I have two asymptotes. Okay? So I'm going to go 3 points, and then I'm going to write an asymptote. That's negative 1. That's undefined. I have 3 points, and I'm going to write an asymptote. That's 1, and that's undefined. And then I have 3 points. I have 3 branches to this graph. That means on your table, you don't have enough room, dude, unless you split your lines in half. So maybe like on your table, you're doing this stuff. I mean, you're crossing these things out, right? And maybe you're like, okay, I've got to give myself some extra room, so maybe I'm either that or you're adding lines to it, or you're doing a table off to the side. You're like, forget this. I'm going to do another table over here, okay? Because you need more points. My question becomes, which ones is it easier to plug my numbers in for x? Is it easier to plug it into the reduced or factored form or the original form?
Original.
And probably original, because there's less places you got to put an x. Here you have to put it in 2 spots. Here you have to put it in 3 spots. So maybe try some values like, I don't know, 0. Let's actually go maybe negative 10, negative 3, negative 2. Then in here, there's 0. So what's in between negative 1 and 0? Negative 1/2 and 1/2. And then 2, 3, and 10. Now when I say don't use your calculator to do these, I mean don't use your graphing piece. You can do the math on your calculator. Okay. So like if I'm putting in that negative 1/2 into my calculator, okay, maybe I'm saying 5, well in the numerator I'm putting parentheses 5 minus 1/2 or 0.5, depending on how you're going to put it in, all divided by, and then in parentheses, 0.5 squared minus 1, okay, and then I have negative 6 that kicks out. Okay, that's when I put positive 1/2 in. All right. Now, if you do second enter, that gives you that entry back so you can edit it. Now just go back in and plug different values in. Put your negative 0.5 in. Okay, so now you have insert and put a negative sign in front. And make sure you add parentheses if you're going to do that here, if you're squaring a negative. Dude, 7 1/3. Negative 7 point, we'll say 3. We'll round it there. Okay, you're going to graph that one. You got some branches you're going to do there. Okay, but if you put it in once and you put it in correctly, then it's just going up and using your insert key and your second enter key. Okay? Questions there? What's the one type we haven't graphed? Where the exponent's greater on top. What type of asymptote will that give us? That's a slant asymptote. Your assignment tonight is to finish the two graphs we did and then try number 14 on your own. Okay? Try number 14 on your own. That will be a slant asymptote. Give it a go. All right? So 11 through 14, right? You've already done number 11. You should have to finish the graph on 12. Finish up the table and graph on 13, and then try all 14 on your own. All right. Very good. Questions? Okay. If you haven't done any of the review, you may want to check that out as well. Woo!